Okay, in this video we are going to be revising CC1. You would have done this way back in year 9. It's just on states of matter, so solids, liquids and gases. And you're going to make notes with me here. You're going to fill in this whole page making notes, and then I'm also going to take you through a few of the knowledge questions which are on the next page. Alright, so we've got solids, liquids and gases. You need to be able to draw the particle diagrams, which are just these circle diagrams. I've drawn solid already because people are generally very good at that. Okay, so I've got all of the particles touching and they are arranged in neat rows. The next one I'm going to do is liquid. I'm going to draw this with you because often students get this one wrong. So liquid, state symbol L, okay, the particles do still have to touch each other. So often I see students drawing in kind of rows like this, but with big gaps between the particles. That's wrong. Okay, you have to have all of the particles actually touching each other. Okay, they're not in neat rows like they were in a solid. It is a bit more random, but they're all touching each other. And you also can't just have a random particle by itself down here not touching anything. Okay, every particle needs to touch. You also can't have these weird little kind of strings coming down the end. That's not what liquids do. All the particles are attracted to each other, so they'll all fill that space, and you'll end up with something that looks like that. Okay, so that would be an example of a liquid. And then your final particle diagram is going to be a gas. This one's easier. You'll just draw the particles really far apart. You'll draw them randomly arranged and you'll end up with something that looks like that. And that is my gas. And my state symbol is G. So make sure you're writing this down with me. Okay, so we need to be able to describe how particles are arranged. Okay, so we've drawn our pictures, but we just need to in words describe how they're arranged. So in a solid, I would say that the particles are touching. Actually, no, I'm going to say the particles are close together. Okay, they're close together. And I'm also going to say that they're in a regular pattern, and by that I mean I've got them arranged in 3 neat rows. For a liquid, okay, the particles are still touching. Okay, so I'm going to write here particles are touching, but it's a bit more random. They're not in nice neat rows, so I'm going to say that they are random. And then for gas, how are they arranged? I'm going to say the particles they're far apart, all right? So they're not touching each other at all. They're really spaced out. And again, I'm going to say they're random. You can just draw dots anywhere you want to. In terms of movement, for a solid, I would say that they vibrate. Okay, so they can move, but they just stay in the same spot and they vibrate. For a liquid, and this is again the one that students get wrong, right? They can move freely, but they can only move freely around each other. So this particle here can't just move over there, okay? And this particle can't break free and move over here. They stay touching each other and they just roll around each other. So we describe this as they move around each other, but they maintain contact. They'll always still be touching. So if you're pouring a drink of water, the particles are just rolling over each other, but they stay touching each other. And then your gases, they can go wherever they want. So they move randomly in all directions. So these guys can go wherever they want. This one can go over here, this one can go down here, this one can go over here. They can go wherever they want in all directions. The last thing we need to be able to compare is energy. So you need to know in which state of matter the particles have the most and the least energy. Alright, well just think it. We're saying that the particles can move randomly in all directions. These ones are just stuck on the spot vibrating. So these guys clearly have the most energy. Okay, so I'm going to say that these have the most energy. So your gas particles have the most energy, your solid particles have the least energy, and then the liquid particles would be in the middle. Alright, at this point I want you to pause the video and I want you to turn over the page and I want you to do questions 1 to 4 and try and do them without looking back on your notes, so you can, if you can give the same language that I did. Alright, so questions 1 to 4 please. Alright, so there's answer 1, okay. You don't need to draw boxes, although you can. You don't need to draw too many particles either. Usually 9 is a good number, and just enough to show the actual pattern. Make sure your liquid particles are all touching something, and that you don't just kind of go off in a random direction. They should all be clumped together. Arrangement and movement of particles. So the arrangement, they're tightly packed, or you can say they're close together, and in a regular pattern. They're all in neat rows. They vibrate. That's how they move. If you were asked to describe the arrangement, you could draw a picture. Okay, I would always draw that picture and then write a few words, because anything you forget to say, you might have forgotten to say regular pattern, but your diagram shows that. So always draw if you're asked to describe arrangement, but in terms of movement, you'll have to describe that in the words. The picture doesn't show it. For a liquid, they are randomly arranged, but they're still touching, okay, and they move around each other, okay. They can't just fly off in random directions. They have to stay touching. They move around each other. And then a gas, randomly arranged, and they are far apart and move quickly in all directions. Again, if you drew that diagram alongside it, and if you forgot to say far apart, your diagram shows that, so you'll still get the marks, but the movement marks you'll always have to write. The next two, I can't remember if I asked you to do these two, but just in terms of energy, in which state of matter do particles have the most energy? We said gases, because that's the ones that they can move really quickly. So in a gas, they've got the most energy, and then least amount of energy, that's going to be a solid, okay. Next thing we're going to look at is just your state changes. All right, so how to move between each different state of matter. So if I want to go from a solid to a liquid, and always just think about water, all right, to go from ice to liquid water, what do? You melt. Okay, so that's melting. To go from a liquid to a gas, okay, if you wanted to go from water to steam, what would you do? You would boil it. So you can write boiling, or you can write evaporating. Either of those will typically be acceptable, boiling and evaporating. And then think, what do we actually need to do in order for these state changes to occur? I'm going to do this in my little red pen, okay? In order for my state changes to occur, I need to add heat. All right, you heat something up to melt it, you heat it up even more to boil it. If I want to go the other way, all right, we'll do this one first, it's a bit easier. If I want to go from water to ice, okay, I would put it into the freezer. So going this way, I am freezing. And then this is the one that people tend to get. If you want to go from a gas to a liquid, you cool it down and it condenses. So it's called condensing. And if I want to go, I'm going to switch to my blue pen. If I want to go this way, I'm not going to say I add cold, okay? I'm going to say I remove heat. All right, you're going to decrease the temperature and you're going to remove heat. Okay, so just make sure you know those state changes. They do come up a lot. The other thing we need to know about these state changes is we need to know that they are all examples of physical changes, and you can be asked about the difference between a physical change and a chemical change. I'm just going to do this here in a little table. All right, I've got physical change and I have got a chemical change. Now, if it's a physical change, no new substance is formed. Okay, so I'm going to give you an example. If I had ice, okay, this formula of ice would just be H2O, and it would be a solid. If I turn that into liquid water, it's still H2O, and now it's liquid. And if I were to boil that and turn it into steam, it's still H2O, it's just a gas. So water is always H2O, whether it's a solid, a liquid, or a gas. And what we can say then is no new substance forms. No new substance forms. When you're changing the state, you're just taking the particles and you're arranging them differently, but the particles are still exactly the same. So physical changes, no new substance forms. The other thing we can say about them is they're easy to reverse. If I want to reverse this process and get back to ice, all I need to do is cool it down. I cool down my steam, it will condense to form water. I cool down my liquid water, it will freeze to form ice. So these are easy to reverse. So your state changes are examples of a physical change, okay, physical change. The opposite of this would be a chemical change. So in a chemical change, a new substance does form. A new substance forms. And if I give you an example that we've been looking at recently, combustion would be a chemical change. It's a chemical reaction. So you might start off with methane, for example, one of your alkanes. You react it with oxygen, and if it's complete combustion, you're going to get carbon dioxide and you're going to get water. So you're turning these reactants into something completely different, and the formula is going to change. Formulas didn't change over here. I wasn't making something new, but the formulas do change here. I'm forming a new substance, and this is much, much harder to reverse. Much harder to reverse. All right, so burning something would be a chemical reaction. If you burn a piece of paper and you form ash, how are you going to get back to that original piece of paper? If you bake cake, that's a chemical reaction. How are you going to undo the baking process and get back to your flour and your eggs and your sugar? Okay, so these ones are much harder to reverse. So chemical reactions are chemical changes. Classic example there would be burning. Alright, so state changes, going from solid to liquid to gas, that's a physical change. Chemical reactions like burning something, that is a chemical change. These ones hard to reverse, these ones easy to reverse. You're making something new, you're not making something new, you're just changing the particles, how they're arranged. Alright, I want you to do questions 7, 8 and 9, please. So please do press pause and actually try and do these by yourself. So 7, 8 and 9. Okay, so there's my state changes from a liquid to a gas. You're going from water to steam. You would boiling or evaporating. So you can say evaporation, either will be fine. From a gas back to a liquid, condensing or condensation. Now, if you're asked to describe the differences, you can absolutely use a table in your exam. It's a really clear way of communicating. So I've got chemical changes and physical changes. For chemical changes, I'm saying a new substance is formed. Physical, no new substance is formed. I've given a second difference. These ones are hard to reverse. These are easy to reverse. And my example of a chemical change is burning, or you could say combustion. Your example of a physical change is just state changes, or you could say going from a liquid to a gas. So give an example of a state change, or just say state change. Okay, next thing we're going to have a look at is heating curves. So I've sketched out this axis here, right? So you can go to your next page. You have another page for notes if you need it. Sketched out this little axis here. I want you to do the same, okay? And we're going to show what happens to water. We're going to use water as an example as we heat it, all right? So on my axis here, I've got temperature. I've got 0 degrees and I've got 100. So I'm going to start below 0 degrees. Okay, imagine I have a piece of ice. I'm going to heat it. And as I heat it, my ice is getting hotter and hotter and hotter and hotter. And then at 0 degrees, I end up with this kind of flat plateau, okay, at 0 degrees. And then I'm going to keep heating it, and it's getting hotter and hotter and hotter and hotter and hotter. And when I hit 100 degrees, I get another little flat bit. And then I keep heating it, and it gets hotter and hotter and hotter. All right? So this is what your heating curve looks like, but we need to be able to label, okay? So below 0 degrees, water is going to be ice. And if it's ice, I'm going to write that it was a solid. So anything below 0 degrees, water is going to be solid. Above 0 degrees, water is going to melt and it's going to turn into a liquid. So I'm going to label all of this part here as liquid. But as soon as it gets above 100 degrees, water is going to boil. And when it boils, it's going to become a gas. And you'll see that when you go from solid to liquid, you get a little flat part of the graph. And when you go from liquid to gas, again, you get a little flat part of the graph. So this flat part here represents an actual state change. So every time it changes state, the graph levels out. So that's a state change, and this part here is a state change. Now we can be more specific with our labels. If I'm going from a solid to a liquid, what is that state change? It would be melting. And if I go from a liquid to a gas, again, what is that state change? That would be evaporating, or you can say boiling. And they can ask you to describe or to explain why the graph levels out when a state change is occurring, okay? So you're heating it and your water is getting hotter and hotter and hotter. And even though you're still heating it, at 0 degrees, it just stops getting hotter for a few seconds. And even though I'm still heating it at 100 degrees, it stops getting hotter. So I'm still giving it energy, but it stops getting hotter. And you need to be able to explain why. So I'm just going to write it down here. When you've got a state change, what is happening? Okay? You're still heating your substance, all right? We're using water, but it could be any substance. You're still heating your substance, but the temperature of the substance does not rise. Okay, so just at this point here, the temperature of the substance isn't rising. Why? Because the heat energy is being used to separate the particles. So usually when I'm adding heat to something, that heat is making the substance hotter. But when it is changing state, instead of that heat making the substance hotter, all of that heat energy we're supplying is going towards pulling these particles apart. So if I'm going from a solid to a liquid, the particles are slightly further apart, and particularly from liquid to a gas, you're properly pulling those particles apart. So all of that heat energy you're supplying is going towards pulling those particles apart. And for that reason, the temperature stops rising during a state change. All right, so I'm going to put this on carousel for you as well. It's probably the hardest question in this topic. All right, I want you to have a go though. You're going to be asked to sketch your own curve. All right, so see if you can do it without looking back at your notes. Sketch a curve and then explain why it stays constant. So just 2 questions there. Press pause, have a go at them. Alright, so this is what your heating curve should look like, alright? It's going from a solid to a liquid to a gas, and as you move from one state to the next, you always have this little flat bit that represents the state change. From solid to liquid, you are melting it. From liquid to a gas, you are evaporating. Why? So by stay constant, I just mean it flattens out, alright? So why does that happen when a state change occurs? Because all of the energy that you're putting in is going to separate the particles instead of making the substance hotter. So usually if you heat something, the heat energy is used to make it hotter. In this case, the heat energy is being used to pull the particles apart. Okay, last little bit here. They can often give you a temperature and they'll ask you what state a substance is at that temperature. And to answer, they have to also give you the melting point and the boiling point. Okay, so I'm going to give you an example. Okay, let's say you've got substance X. Okay, and substance X has a melting point of 60 degrees Celsius, and substance X has a boiling point of 150 degrees Celsius. They want to know if it's a solid, a liquid, or a gas when it is 20 degrees Celsius. Okay, so if the temperature is 20 degrees Celsius, 20 is lower than the melting point, 20 is lower than the boiling point, and if it's lower than both of them, it's going to be a solid. Okay, so X at 20 degrees is going to be a solid. If they give you a different temperature, all right, if they said, right, well, what state is X at 100 degrees Celsius? Okay, now I'm looking at 100. 100 degrees is higher than 60, but lower than 150. And if the temperature they give you is in between the melting point and the boiling point, that's going to make it a liquid at room temperature. Sorry, a liquid at 100 degrees Celsius. Other thing they could do is they could give you a temperature like this, 200 degrees Celsius, all right? So 200 degrees is hotter than 60 and it's hotter than 150. So if it's above the melting point and it's above the boiling point, then it's going to be a gas. Okay, so they'll give you a melting point and a boiling point, then they'll give you a temperature, and you just need to see, is it lower than both? It's a solid. Is it in between? It's a liquid. Is it higher? Then it's a gas. Now I'm going to give you one of these to do. It's slightly harder because I've given you negative numbers, but see how you get on with it. Again, please do press pause. Have a go at this by yourself, all right? So 12, 13, and 14, you're just answering me solid, liquid, or gas, okay? But just pay attention to the fact I've always given you negative numbers. So just be asking yourself which temperature is hotter. Alright, so if you have a look at the first one here, they've given you the melting point, they've given you the boiling point, and then they ask you about minus 240, okay? Minus 240 is colder than minus 220. Okay, minus 240 is also colder than minus 112. Okay, so it's a lower temperature than the melting point, it's a lower temperature than the boiling point, and that means it's going to be a solid. Okay, if it's below both, it's going to be a solid. So just pay attention to the negative number, minus 240. Think about it in money. You would rather have minus 112 pounds than minus 240. Okay, that is a worse situation to be in. It's a lower temperature, so it's below both, it's going to be a solid. The next temperature I've given you is 20 degrees Celsius. All right, so 20 degrees Celsius is hotter than minus 220, and 20 is hotter than minus 112. So if it's a hotter temperature than the melting and the boiling point, then that means it is a gas. And the last one here, minus 150. All right, so minus 150 is hotter than minus 220, but minus 150 is colder than minus 112, and if it's right in the middle, it's a liquid. Okay, that's the worst case scenario if they give you negative numbers. This is a bit easier if all the numbers are positive, but we need to be prepared for everything. In the lesson, we're then going to just do all of the exam questions that have come up on this. All right, there's a carousel to do as well, so make sure you do that. But if you come into me knowing the basics of this topic, which is what we've just gone through, then we can kick on, do all of the exam questions in the lesson, and make sure we have nailed this topic by the end of Monday.